So revision of module 5 for physics is advanced mechanics. And this really can be more or less made up of two main components. One is projectile motion, which we'll be going through first. Another is circular motion. And then once you do that, then the rest is just basically application to, everyday examples. And that includes, just normal everyday situations, but as well as, sort of everyday situations like car going around bends and so on. But you also apply it to, your satellite calculations, like your orbital velocity, escape velocity, and so on. So, your escape, orbital velocity, and so on. All right. Now, I will not really be revising your year 11 things here, unless, unless all of you or a vast majority of you need it. I'm going to basically assume you know your year 11, and you do need to know that, okay? So your assumed knowledge for this section is, very, very applicable to this topic, is going to be all the stuff from module 1 and module 2 of year 11. So, F equals ma, your forces, what type of forces they are, which direction, and, as well as your module 1, right? But probably more module 2 than module 1, right? Your module 1, you'll need to know how to separate out into components and vectors and components and things like that. But probably it's more module 2, like your forces and also your energies. Less so for momentum. You're not tested on momentum as much here. Okay, so I am assuming you know all of those things from module 1. Now, if it is unclear, do let me know. But because you may have everyone else maybe in a similar situation. But for now, I'm basically going to assume that hopefully you're reasonably comfortable with your year 11. Okay, so starting with projectile motion. So what is projectile motion? Well, the definition of projectile motion is that, of course, it's the motion of a projectile. Now that is not very helpful, obviously, because, well, that's quite clear. You just rearrange the words. So the real question, therefore, is really, what's a projectile? And for your course in physics, we're basically saying that a projectile is an object that falls under gravity. Only, okay? So basically, it's only affected by gravity. So we are ignoring air resistance. So air resistance might exist in real life, but for your course in physics, we're ignoring it. If you're doing 4-unit maths, that might not be the case, but we are ignoring air resistance here. And your motion of your projectile, there are no other forces except gravity. So, what sort of things would, what other forces might you have if you throw an object in the air? So if you have a plane, it's got wings. The wings will lift the plane up. So the plane is not a projectile. So, a plane is not a projectile. Even if the engines are off, it still has wings. So plane and gliders are not projectiles. Rockets are not projectiles because, well, obviously, it's like a plane with its engine is on, right? So rockets are not projectiles. So basically, what is a projectile? A projectile is something that once you throw it or launch it, then it just falls under gravity and only gravity. So the important point is it falls under gravity and only gravity. Okay. Now, I know not all of you do 4-unit maths or 3-unit maths, so I'm not really going to derive things mathematically here. I'm just going to mostly focus on the results and the techniques. But for those who do, you know, 4-unit maths and have that mechanics section, then all of these results can be derived, you know, mathematically through calculus and so forth as well. All right. And you might use sort of vector notation to do it. We won't be doing that here. Okay. So it falls under gravity and only gravity. And the thing with that, so examples of projectile motion would be, for example, if you were to throw a ball, you throw or kick a ball or hit a ball, same thing. All right. You could, you know, basically things like cannonballs that are fired or bullets, and not 100% accurately, but arrows are kind of close enough. So common, like arrows have feathers at the back, which, but we'll assume they're all just projectiles. And basically, if you've got someone jumping, right, something launching themselves, so, you know, so a person jumping, and that could be a situation like, you know, they jump off like a, you know, they jump off a ledge to the lower level or something like that. Or, you know, there could be sort of like long jump. If you're doing sports, long jump, high jump, you know, shot, you know, throwing a ball such as shot put, or, you know, javelin, although that's not technically accurate, so I'll leave it out. But basically, these are all examples of projectile motion, all right? So given that a projectile is only going to fall under gravity, and it's basically free fall in 2 dimensions, and in projectile motion, we normally launch at some angle V with some angle theta, all right? And that then allows us to basically, you probably are quite familiar by now, that it will go through this sort of path here. And so the important thing is we then rely on Galileo's analysis, which then basically says that projectile motion can, I mean, it's obviously a 2-dimensional motion if we throw it with some sort of angle, but projectile motion can be considered as 2 separate 1-dimension motions that are independent. So we're basically saying that the horizontal and the vertical are independent, all right? And so that we're saying is that we can do it, you know, so we can, you know, consider the horizontal motion, which is 1 dimension, and your vertical motion separately. All right. And really, this then just relies on your sort of module 1 kinematics, where basically you use your formulas, you know, V equals U plus AT, S equals UT plus half AT squared. You don't really use the V squared equals U squared plus 2AS here, although I'll just quickly write it out for your revision. Okay. So we basically are using these formulas in 1 dimension separately, all right? And that also then relies on your skill in module 1 to be able to separate out components. You know, your technique is to be able to separate out components. And the thing that allows us to do that is, you know, Galileo's analysis of the fact that we can separate into, you know, horizontal and vertical components and just look at it separately. And you can most definitely get, you know, multiple choice questions about that. You know, they might ask, you know, what did Galileo's analysis say? And then we'll give you a whole bunch of choices, including, you know, the right answer and, you know, stuff like whether they'll hit the ground at different times and so on, and which is not really what they're talking about there. All right, so we'll need to start introducing some terms here. So we'll launch at, most books seem to use U, so I'll use U and I'll kind of do that. Doesn't really matter, but U is what we'll call the launch or projection velocity. And theta we'll call the launch or projection angle. Now, you can probably see at t equals 0, that means your initial velocity is at angle theta with, magnitude u. And from year 11, hopefully you can see that you can use trigonometry, and hopefully this is not too difficult for any of you, to split it into a horizontal component and a vertical component. So this is the horizontal, and this is the vertical. And the horizontal component will therefore be u times cosine theta, and this is going to be u times sine of theta. Okay. And so it's important to note that if we're using capital U here, then at t equals 0, then the horizontal velocity which is the initial horizontal velocity, which in physics is usually given the letter ux, is going to equal, u cos theta. And your vertical initial velocity is going to normally given the term uy, which is going to be u sine theta. And we basically just do that using year 11 work, right? We just take this situation, we just draw out the velocity vector, and we split it into your horizontal and vertical using your trigonometry. So we'll keep that in mind, and we'll do that on the next page now. And we'll kind of do things. I might go a little bit faster to make sure we can go through things, and hopefully this is all things that you're familiar with. But basically, we will look at things horizontally, and we'll look at things vertically. Now, in terms of forces, we'll remember that we are under gravity only. So if you think of your free body diagram, that we're saying the only force is weight, which is mg. So horizontally, the force, there's none. There are no forces. But vertically, will equal weight downwards. We'll set downwards to be negative and upwards to be positive. It's a vector after all. So you need to set that. So what we then basically have is it's equal to negative mg. Now remembering that acceleration equals F over m using Newton's second law, that means acceleration in the x direction is just going to be 0 because there's no net force. And the acceleration in the y direction using, F equals ma is just going to be F divided by m, so it's negative g, which means that it's going to be downward. The next thing we'll need to consider is velocity. And for that, we'll use the sort of formula v equals u plus at and sub in the appropriate values. And we'll find that because acceleration is 0, vx is just equal to ux, which, if you like, is just u cos theta. Vy, on the other hand, is going to be uy minus gt, which, if you like, is u sine theta minus gt. And your displacement will rely on your formula of s equals ut plus half at squared. So we're really just subbing things in for each thing. So sx must equal uxt, plus 0, so nothing. And, that's, in other words, u cosine theta times t. And your sy would therefore equal your, uyt minus half g t squared, which would therefore equal u sine theta t minus half g t squared. And then depending, you might have a plus h. Depending on if you start from lower, depending where you set 0, 0, you might start from, this is the situation if I start from ground level. If I start halfway up, then, it will be a bit different. Okay. Now, what we have then is those are our formulas, and we'll basically be using these formulas to do projectile motion questions. All right. So those are our formulas. And you do need to sort of, these will be on your reference sheet, but you can kind of get them quite clearly, and you can see that. But just the key point to note, of course, is that your horizontal is going to be separate to your vertical. Okay. It's all great to know those formulas, but what we're really often being asked to do is to calculate things. All right. And so you need to basically be aware of all your terms. So I've already talked about the terms of what u and theta are, so I won't rewrite them out again. But you should also note, of course, that your projectile will reach some sort of maximum height, which I'll call h, and it will also land somewhere. And that distance is what we call range. It will also take some time to fly that far. So it's going to land at some time, which we can call TF, and this is equal to the time of flight. So these all are three standard things that, you may need to find. Okay, so we'll need to talk about the techniques for finding them. I won't do any of the working here. I'll just tell you the how, because the working is, usually not relevant for physics at the algebraic level. You would generally be doing this with sort of numbers in physics, but you need to understand the technique. So to find the time of flight, what you basically need to do is 1, let y equal 0, solve for time. Okay, so basically you're saying at what time is it on the ground, and you should notice that you'll get two answers. Okay, one at the start and one at the end, and so you'll get a quadratic, and we basically use the sy kind of thing. Let sy equal 0, solve for t, and obviously we'll sub in the appropriate values for u and theta and all that kind of thing. And then so obtain two answers, and then eliminate the t equals 0 answer, or or if you're starting in midair, or the negative answer. If you're starting in, if you're not starting from level ground, you might start here, then you'll get a positive answer and a negative answer, and that's how you find time of flight. Just let y equal 0 and solve for t. It'll be a quadratic, but hopefully nothing that you can't handle. To find the range, your first job is to find the time of flight. And we've already covered that, so I won't redo that. That's here. So find the time of flight first, and then sub the time of flight into Sx. All right. So just so you know, the time of flight for level, I'm giving you level ground, okay? So I don't need to memorize these, but I'm kind of just going to give you the results so you kind of know what to expect here. So because you're going to basically use the fact that, this is equal to 0, the time of flight, you're going to use these formulas, yeah? And you're basically going to get 2u sine theta over g. You don't need to memorize them. It's the technique that's important. I'm just telling you what sort of thing to expect here. All right. Now, if you were to sub time of flight into Sx, you should find that the range is going to be u squared sine 2 theta over g. Right. And to find the max height, firstly, you would need to find the time at max height. And you would do that by, finding t when Vy equals 0. Because basically, as you go up, your vertical velocity gets lower and lower until it stops. And when it stops, that's when it's at the max height and it's going to go negative. So basically, you solve for time when Vy equals 0. And you should find that Ty there. Let me give myself a little bit more space here. So for level ground, you should find that the time of flight would equal u sine theta over g, all right? Just so you know, like, I'm boxing these results to give you an idea, but, you know, don't memorize these results for physics, all right? Because, you know, you're not allowed to use them, right? What you need to be focusing on is how to do it, all right? You can't just go, oh, I know it's that, and just sub it in the formula. You can't do that. You're not going to get the marks, all right? You need to actually show it. All right, so find time of flight at max height, and then sub that time into your SY, and then you'll find that H must equal V squared sine squared theta over 2G. So it's very, very important that you do know exactly how to find any of these things for, you know, like for given numbers, like, and focusing on the steps. So not the formulas, but the steps. Because these are very, very, very standard questions that, you know, you need to be able to do for projectile motion. They're extremely standard. All right, so we can prove this mathematically and so forth, but there are some sort of results that, you know, you can sort of take away. And I'll write out the results here, you know, assuming level ground. So hopefully the formulas will help you see why they're the case. But, you know, I'm not telling you to remember the formula. I'm saying that you have to sort of focus on right. So those are sort of the formulas on the right-hand side, which may help you understand why, what I'm about to say. But let's start with range, all right? So the results you can get from this is that, you know, obviously as velocity goes up, range goes up. Common sense will tell you that, all right? If you're on a different planet, if G goes up, range will go down. Common sense will tell you that too. So note that we just corrected that that's over 2G, okay? It won't make a difference to our sort of assumptions that we're going to be looking at, because 2 is just a constant, but yep, that is now the correct formula. So for range, you've got as V goes up, R goes up, as G goes up, R goes down. Now, obviously, I'm assuming everything else is constant when I change one thing. Now, as I vary theta, then you can see that max range occurs when sine 2 theta equals 1. In other words, theta equals 45 degrees. Okay? And so, and the maximum range will also equal V squared over G, or U squared over G. Okay? So, some basic ideas: as V goes up, R goes up. As G goes up, R goes down. If we change the theta, we can get a maximum range of U squared over G, and that occurs when it's 45 degrees. And also because of this and so forth, for any range less than the maximum range, there are 2 angles for that can hit that range. And these angles are complementary. So we're not really deriving the results, I'm more or less just telling you, and these used results can most definitely be helpful when you're doing certain questions, right? So having an understanding of this. So, you know, I'm basically saying that if we can sort of hit a target like this, then we can also hit a target like this. And, you know, we might have two different, you know, not the best diagrams here, and zoom's playing up a little bit. So you'll have to bear with how it's moving the lines around a bit. But we're saying that if this is beta and if this is alpha, then we're saying alpha plus beta must equal 90 degrees. Okay. All right, so that's the key things about range I wanted to say. So as V goes up, R goes up, as G goes up, R goes down. If we change the angle, 45 degrees gives you max range. And for anywhere that's not max range, you can hit with two angles. One's the sort of low version, and one is the high angle version. So the path will be different, but they'll hit the same spot. Let me use a new page for the next one, given that it actually took up a bit more space than I thought. All right, so if we examine max height, common sense will tell you as V goes up, H goes up. As G goes up, H goes down. And as theta goes towards 90 degrees, H goes up. And obviously the max height will then be, you know, the max height, the maximum of the max height will be, you know, but usually they don't ask this, but, you know, is when you just throw it straight up, right? Usually this is not so important compared to maximum range. So that's the results from max height, all fairly obvious here. And if we compare, you know, time of flight, you'll probably notice that as V goes up, time of flight goes up. As G goes up, time of flight goes down. And as, you know, as theta goes towards 90, time of flight becomes longer. And if you quickly compare these, you'll notice that as far as direction of the relationship goes, they're all the same, right? You know, as this changes, both go up. As this changes, both goes down. As this change goes to 90, both go up. And so another important point you might realize, and I'm not going to prove it mathematically, but you can do so in your own time if you feel so inclined. I mean, I won't bother for physics, but, you know, if you're algebraically inclined and you're happy to, then basically for any projectile with the same max height, it will have the same time of flight. You can mathematically prove that there is a relationship between h and t. They're related by a constant. Okay, so basically, if you've got a projectile, I don't care how you got it to that height, but as for projectiles that are launched from the same position and that reach the same max height, they'll have the same time of flight. So what am I saying? I'm saying that if I have, you know, ground level, and let's say I've got some sort of maximum height level, and let's say I've got different projectiles, so they're all launched from here, but, you know, at different velocities and angles. So one is like doing that, and it's going to land somewhere sometime. One is going to do this. You know, one is going to do this. Well, let's make it a bit more symmetrical. And one is going to do this, say. So we are saying that all the projectiles have the same max height. Therefore, we know they must therefore the same time of flight. In other words, if launched at the same time, then they will land at the same time. Now, I'm clearly, they're launched at different angles. And because they're reaching the same max height and with different angles, then they launch at different velocities as well. So, you know, so this one's probably, the blue one's probably launched at the highest velocity. But the fact of the matter is, since they've got the same max height, then they must have, you know, the same time of flight, without a question. Okay. So that covers the key main things that you're going to be tested on with projectile motion. But there's probably something that's tested less often that we still need to talk about. Now it is tested, it's not tested, it's just comparatively less often. So I don't want you to think that it won't be tested, that's not the case. So you are comfortable with the fact that, you know, let me just quickly and briefly write out some concepts again. So firstly, we said that, you know, acceleration equals 0, ux equals u cos theta, and sx equals ut cos theta, and the vertical is going to be, you know, ax equals negative g, ux equals u sine theta minus gt. You know, sx must equal ut sine theta minus a half gt squared, and maybe with a plus h if you're not starting from the origin. So what I probably didn't stress enough, and this is very commonly tested, what I probably didn't stress enough is what, you know, what you can tell from these. I mean, it's quite clear from the equations, hopefully, but horizontally, there is no acceleration. This is a constant velocity and a linear displacement for the horizontal. Whereas for the vertical, what you end up having, so this is the horizontal. For the vertical, what you've got is a constant acceleration, and so the acceleration doesn't change, but a linear velocity that does change, you know, going up and going down, and then you have a quadratic sort of displacement. And so these concepts are very commonly tested. You know, they might ask you that in words, they might ask you that in graphical form, but you need to be very clear about what they're asking for. Are they asking for acceleration, velocity, or displacement? And are they asking for the horizontal or the vertical, or a mixture of the two? Okay, but what I've covered just now is actually very commonly tested. Now, what is probably, now I'll kind of minimize that a little because I need the space and I don't want to redraw it out, but hopefully you guys can still read that without too much trouble. All right, so that's important. Now, what is less commonly tested, but is still tested, is about velocities in midair. So you guys might know from just, I guess, your general things by now, projectile motion, and this will apply to circular motion as well, is that if we're looking at velocities, you know, at this point in time, at the start, then we've already said it's like this, you know, this magnitude and this direction. But if we're looking at somewhere in midair, then you hopefully know that basically, you know, you're taking a look at the sort of, you know, tangent to the curve kind of thing. Maybe I've drawn it a bit too long, but basically we're drawing like tangents to the curve. And so you can see that the velocity direction will change, and quite clearly your tangent at the top is horizontal. So you only have horizontal velocity at that point, but then the vertical velocity starts going downward and you kind of have this sort of situation. So all of you, I assume, are doing at least 2-unit maths. So hopefully that, you know, relates to your 2-unit maths sort of kinematics, and I assume you've all done that at this point in time. So hopefully that's not giving you too much of a problem. So this is like, you know, instantaneous velocities, or, you know, diagrammatic representation of instantaneous velocities in midair. And you can quite clearly see that the direction is changing. Now, what you might be asked is to find the velocity, whether you are asked to find the magnitude or the direction, or both, of the velocity at some particular point in time, t. So not at the start, not at the end, not in the middle, not at max height, which is also done. And note that over here, you only have horizontal velocity only at this point, which of course means that the velocity here will just equal u cos theta, because, but the point is, if you've got it in midair, then you might be asked to find the velocity component, like the total velocity, both the magnitude and the direction. Now, if you don't know how to do this, it's actually a lot simpler than you think, because the velocity component is, as always, a two-dimensional here, made up of both a horizontal component and a vertical component. Now, the horizontal component is, Vx, the vertical component is Vy. So basically, the way to do this question is basically, one, find the horizontal and vertical components separately. So, they ask you, okay, at a particular point in time, like t equals 10, what's the velocity and direction of the projectile? So you basically just use the formulas here, sub in t equals 10. Well, we know the horizontal, that's never going to change because it's constant. But we'll need to sub in t equals 10 to get the, I should have written v here. But anyway, we'll need to sub in the velocities. We'll need to sub in the time to get the velocity of uy. So basically, we're saying find Vx and Vy. And then for step 2 on the left, what you would then do is use Pythagoras to find the magnitude. So in other words, we're saying that the velocity at any point in time is always Vx squared plus Vy squared, but you just need to find the Vx and Vy at that point in time. And then your direction is use trig to find the direction. So for example, if we call that theta, then theta must equal, tan theta must equal, the absolute value of Vy over Vx. Okay. And that's projectile motion. Remember, what you really need to be clear on when you're doing projectile motion questions is, apart from the conceptual questions, is how to use these formulas. These formulas are all in terms of t. That's a pretty important point. So whenever you're using these formulas to solve things, which is what you rely on in physics, then you'll have to get them in terms of time. You're always thinking in terms of time. As far as mathematics goes, this is called your parametric equations, all right? But you'll need to always get the time and then sub into the appropriate thing. So regardless of whether you're trying to find range or max height or anything, you're basically thinking, how do I get the time for that? And then what time, which formula do I sub in? And you can see that when we did range, max height, and so on. So that's basically everything for projectile motion. And it'll be time to move on to circular motion now. Now, circular motion is, as you might expect, when an object moves in a circular manner, we call that circular motion. I'll just simplify that to when an object moves in a circle. Now, it may hopefully be clear by now, but if we've got an object going around in a circle, then based on what we said a bit earlier, the velocity is always going to be, drawn at a tangent. So it doesn't really matter if this speeds up or not. The speed might not change, but the velocity will always change. So note, the velocity is always tangential to the circle. Without question. And that means, or even if the speed does not change, and in physics, you're not normally going to be doing any questions where the speed changes. It does mean, however, that the direction must change, because you can see that it's, well, not going to be doing the, not the same direction, right? So as a result, direction must change. But because direction must change, because velocity is a vector, therefore velocity must change. Not necessarily the magnitude, i.e. the speed, might not change, but velocity itself, being a vector, including direction, must change. And therefore, that means you must have acceleration. And so the acceleration, which we could prove mathematically, but we won't for our purposes, it must exist. You cannot have circular motion without acceleration. And so the acceleration is called, it's given the term AC, which is called centripetal acceleration. And this is basically the acceleration required to undergo circular motion. Now, this is always towards the center. So centripetal, the meaning of that means towards the center. That's why velocity is always tangential. Acceleration is always centripetal. And if that word's a bit difficult, then think towards the center. So in other words, this is the velocity direction. This is the object, moving. But in the diagram, we would then say that this is going to be towards the center. So this is the acceleration at each point. And they'll all be pointing towards some sort of, center. And I know you guys don't do circle geometry, technically anymore, but it may also be helpful to know, if you don't know already, that a tangent and a radius of a circle are always at 90 degrees. So the relationship between these two is always 90 degrees. So that might help explain, when we do talk about sort of circular motion with particles in magnetic fields, that might sort of help you understand why that's the case if you're having trouble with that. But the key thing with circular motion is for an object to move in a circle, its velocity must, by definition, essentially change. The velocity is always tangential and therefore change. That means you must need acceleration, which can be proven to be centripetal and is always towards the center. We can always also prove that the centripetal acceleration, the magnitude is v squared over r. And you may instead see this written as r omega squared, where v is velocity, measured in meters per second, and omega is angular velocity, measured in radian per second. Now, importantly, it's still acceleration, right? So you're still looking at module 1, module 2. Acceleration, to get acceleration, you need a force, right? To accelerate an object by Newton's second law, you need a force. So centripetal acceleration is v squared over r equals r omega squared. Now, but we know this has to come from a force. So because F equals ma, then Fc, called the centripetal force, is basically just going to be mv squared over r equals mr omega squared. So this is the centripetal acceleration. And this is the centripetal force. Now, one thing that you really should be very paying much attention to, Fc, the centripetal force, is the force that is required to, accelerate, to provide the central acceleration, to basically, to move in a circle. Now, very importantly, it's not a force itself. So what do I mean by that? And this is something that confuses quite a few students. And so what I'm really trying to get at here is that, well, if you've got a centripetal force, what you've calculated is what you need, okay? If an object is moving around in a circle, it will clearly it will, need a centripetal force, all right? It does. But what I'm saying is that centripetal force is not a force in the sense that, your forces from module, 11, from module 2 is, so it's not like, actual forces are things like, weight, tension, friction, etc. All right, those are actual forces. Centripetal force is not a force, it's just the force that you need. So it's kind of like a cost, right? And this is quite important, centripetal force is essentially the net force, right? Or if it is going in a circle, the net force must be the centripetal force. But what I'm saying is centripetal force does not provide any force itself. So it's a bit like if you want to buy something, you want to go to the shop, you want to buy, I don't know, some food, right? It costs, say, $20, right? Now, if the shop says that it needs $20 to buy the food, you don't automatically have $20. Okay, you don't automatically have $20. I mean, if you have $20, you can, give a $20 bill across and you've got the food. But you need to actually have that $20. If you don't have it, you don't get the food, right? Now it might not be $20 cash. You might be paying $20 with card. You might be paying $20 with, PayPal or Alipay or whatever you want. Or you might make up that $20 by, hey, I've got a $5 discount voucher and $15 with card. Or you might say, I'll pay $10 with card, $5 with cash, and $5 with a note, and and the rest in coins. But the point is, no matter how this cost is made up, you need to actually make it up with actual things. So just like, we need to actually pay with actual money in some way, the centripetal force is just the cost, and it needs to be made up by, by actual forces. So if an object is undergoing circular motion, then the net force must equal the centripetal force. This is the net force. This is the centripetal force. Okay. So it's kind of like saying, okay, I see you have I see you bought that food. You must have paid the $20, right? It must be true that you happen to have enough money to buy it, basically, right? And that basically is all you need to know for circular motion, really. I mean, that's really the crux of the issue, all right? The rest of circular motion, there's really no extra theory. Now, what you do need to know from module 2 and module 1 is, how to, so, we might do an example question, hopefully, but basically it's how to break down into components. So, it will probably still be horizontal or vertical, but make sure that whenever you're breaking down into components, it will always be one is towards the center, and the other will be perpendicular to that. So probably tangential. And very commonly, that's also done, you know, in terms of horizontal and vertical. Just make sure that one of them includes a direction towards the center, all right? So you need to know how to sort of break down into components. You need to understand your F equals ma formula from module 2, but then really circular motion after that is really just, you know, using, it's really your year 11 question in module 2, but done with this idea, okay? So I'll just make up the question and then, you know, we'll, but as far as theory goes, that's circular motion in terms of theory. Okay? So hypothetically, let's say I've got a string and I've got an object, and this object is undergoing circular motion in the horizontal plane, so looking something like this. And it's kind of going around in some direction. So it's kind of tracing around a circle. So, you know. All right. And let's say that this object, you know, is swung around in a circle. And we can give you different things and ask you to work out different things. Let's make this 30 degrees, all right? And let's say, you know, let's say I don't know R, like R is unknown. I'll just, you know, different questions may make different things unknown. So I might say that the, you know, the object is moving at, let's say, you know, 10 meters per second is probably too fast. Let's say, oh, no, 5 meters per second in a circle, in a horizontal circle. And the string makes an angle of 30 degrees with the vertical as shown. Find the radius of the circle. All right, so we might do something like this. Okay, could be an example question. Now, the way we do this question, as I keep saying, is no different to the way you've done year 11 questions in module 2. So what does that mean? That means the first thing you need to do is draw a free body diagram. And so your free body diagram, you know, you'll need to think of your object and you need to think of what forces act on it. Now, I said before, lots of students go, well, there's a centripetal force acting on it. That's not a force, okay? You can draw in the net force. You can understand it's the net force if you like and draw it with a dashed line, but you need to understand it's not a force. It's the result of the sum of forces, but it itself is not a force. So given that I've said, you know, this object is swung around by a string, hopefully it won't be too hard for you to understand that there is a weight force going downward from year 11, and that there is a tension force pulling this way. Because, you know, it's, you know, acting along the string. That's what the tension force does. And so now we've got our free body diagram. The next thing you need to do once you've got your free body diagram is, well, break it down because it's 2 dimensions. So you need to break it down into horizontal and vertical components. So because one direction, as we said, must always go towards the center, one of them must be, you know, left, right kind of thing. And the other one, you know, in this case, we'll pick up, down. So we'll pick horizontal and vertical for this case. Now, as with always, when we're splitting things up, you know, you want to set your sort of convention. So in my case, I'm going to call left positive because that's towards the center. It doesn't really matter, but, you know, I'm going to call the right negative. It doesn't matter, but I'll just do that to make it easier. I'll personally call towards the center positive. and up is positive and down is negative. And we'll notice that your weight force doesn't need splitting. It's already in one direction only. But my object, my tension force needs to be split into the left and up. So, you know, this is tension in the horizontal direction and this is tension in the vertical direction. Now we'll note that this is 30 degrees. And hopefully it's easy to be able to see that tension in the horizontal direction is T sine 30, which you can simplify to T over 2. And tension in the vertical direction is going to be T cosine 30, which you can simplify to root 3 T over 2. Okay. So this question, you know, probably would be worth a few more marks in a physics exam because I haven't led you through it at all. You know, in terms of the question hasn't got like a part 1 or a part 2. Could they ask you this in a physics exam? Yeah, they could. Will it be worth like more than 1 mark or 2 marks? Yeah, they would. Probably be worth about, you know, towards 4. Okay. And it's probably towards one of the harder questions that you might get in, you know, physics, if you know, if they didn't lead you through it at all, like this. If they lead you through it by breaking it down for you, like go, hey, draw out a free body diagram and so on, then, you know, it's your regular standard question, but then would have broken it down into parts, so it might be easier for you to do it. But the marks will still add up to, you know, 4 or something, maybe a bit more, depending on how generous they feel. Anyway, so now we've broken down the parts. Your job now is to sum them up in the horizontal and vertical direction, kind of like what we did for projectile motion, except we all know what the forces are for projectile motion. So we'll need to do horizontal, and we'll need to do vertical. Now, horizontal is easy because there's only one. So that's tension horizontal, which is tension over 2, and that's the sum of forces. And if you think about it, you need to think about the fact that sum of forces must equal MA, right? But if you think about what's happening horizontally, it's, oh, wrong way around, but doesn't matter. It's going in a circle is the point. It's going in a circle. If it's going in a circle, then that means the acceleration is centripetal acceleration. Or basically, I'm saying that it has to be equal to centripetal force. And so what I'm basically saying is that T over 2 must equal FC, which must equal mv squared over r. Now, one thing I probably should add that I appear to have forgotten is the mass of the object. So I will just say that the mass of the object is 3 kilograms. Okay, I appear to have left out that information that I will need. So this T over 2 is the, you know, we're doing horizontal, right? So we've got 2 forces only. This is vertical, so there's no horizontal component. This is diagonal, which has a horizontal and vertical component. So if we're looking at the horizontal aspect, then it's only the, you know, horizontal component of tension only. In all my forces in my question here, where I only have 2 forces, you could have more, you know, you could have friction as well, but in my question here, there's only 2. That's only the horizontal component, which we've already worked out to be T over 2 using, you know, T sine 30. So what we're really doing here is that, you know, we're summing up things horizontally, and that's the sum of the horizontal forces. That's the net force, you know, looking at the actual forces. So that's the net force. And this is the result of the net force. The net force must produce the horizontal acceleration, which, because it's going in a circle, must be central acceleration, which means it must be the central force, which is, you know, mv squared over r. Now we don't know r and we don't know t, but, you know, we'll see in a moment. But we do need to know m, and, you know, I should have said that at the start of the question. I just made up 3 kilograms here. All right. Now let's also do the same thing for the vertical. So vertically, let's have a sort of slight divider line here. So vertically, what we're going to have is, because up is positive, you're going to have TV, it being positive, and then you have to minus W because, you know, weight is going downward. And so because you've got TV minus W, then what you end up having is, well, that's the net force equals MA in the Y direction, of course. But if you think about what's happening to this particle as it's going around in a circle, which is horizontal, you need to think about what's happening to this particle sort of vertically. You know, is it accelerating up or down at all? And so that's what you really need to think about when you're examining this question. And if you think about it for a little while, hopefully you recognize that in my situation here, this thing is staying, horizontally. So, if I draw it as a sort of 2D diagram, it's going to stay, it's going to move left, right, but it's never going to move it up, down, right? And this is a 3D diagram, but if I did it as a 2D diagram, it's just going to kind of go here, 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 here. It's not going to, it's going left and right. It's not going up, down. So what we're really saying is that that's going to be 0. Okay. Now, it's very rare in physics for you guys to have this not be 0. It is possible, okay? And you'll get, that means you'll go around in a circle, but it'll go up. So that's called a helix. And you could do that. And, for more complex questions, you might do that. And you might be, but for the vast majority of questions that you get, the vast majority, one of them will be centripetal acceleration, centripetal force, because it has to be, because it's in a circle. And the other one will just be 0 for the vast majority of questions you get. Now, what that then allows me to do is sub the TV, which is root 3t over 2 minus w equals 0. And that lets me get t must equal 2 times w over root 3. Okay. And so, because w is just mg, and you should know how to work that out, w must equal 3 times 9.8. So we can get w as a number, right? And that will be, 29.4. And so basically we can sub that w in on the left and then, multiply by 2 over root 3. And we'll get tension equals 33.95 newtons. And so now we've worked out the tension in the string. And given that the tension in the string being the, the total tension, we can then use that and sub that in here. So in other words, let me do this because I'm running a bit out of space and because letters take less space than numbers. I'll just rearrange. Hopefully you guys are all happy with the algebra. So because what I'm trying to find is r, remember? I'm trying to find the radius. So you can sub numbers in now if you prefer numbers, but because I've got lack of space, I'll just keep it all as letters for now. So, and I will just do the algebra hopefully relatively quickly. Okay, hopefully you guys don't have trouble with the algebra. I'm just, moving r across, moving the t down, moving the 2 across. So I'm saying r equals 2 times the mv squared over t. All right. You sub in your numbers. So remember, your velocity is 5. Now I've given it to you in meters per second. Be very careful with units. Okay. Your units, when you're using these formulas, must be in SI units. So that's meters per second. If they gave it to you in some other unit, like, centimeters or kilometers per hour or something else, you need to do conversion. We don't need to do that here, but, if you did get something in different units, then you have to, you have to convert. So in my case here, that's just going to be 5 squared. All right. And then divided by the tension I worked out earlier. All right. And if you use a calculator, then apparently that's going to give me a radius of 4.42 meters. And that will be the answer to this question. This question asked like this is probably, towards the harder end of what you might get in physics. just because there's no lead through at all. They just give you information and say, find it. You know, physics is likely to, you know, just ask you more basic things, like, you know, find the components one by one and then lead you through it. So maybe this will be like a part 1. Maybe this will be like a part 2. Maybe this will be a part 3 or something. But they could and have done, you know, just give you a question and just, you know, and just work it out. And that could be worth, like, you know, I'd say something like this would be worth minimum 4 marks. It'd be around the range of 4 to 5. Depending on the complexity of the question, maybe 6. It might make it, you know, it could be more complicated if, you know, yeah. So, you know, how you do any circular motion question is exactly the same. It doesn't really change at all. It uses the same theory, it uses the same techniques. You draw your free body diagram, you break it down, you sum them up in each way, and you know, do algebra with it. The forces may change depending on the situation. So in this situation, it's just tension and weight. You know, you might look at, say, bank track situations, but all that really, you know, changes in that situation is that, you know, you've got your object on a bank track, and I'm drawing a 2D diagram. It's going in a circle like this. So it's not really different. It's still circular motion, but what you have in that case, you've got weight, you've got normal, and you've probably got friction, you know, pushing either to the outside or inner, depending on your velocity. So it's the same sort of analysis, just different forces involved. So I will leave you to do that, and, you know, I will rather cover the other content, but this is really just application of the theory we've talked about. So in terms of steps, as I said, you know, 1, it's just like at year 11, you know, identify all forces. And that includes, you know, their magnitude and direction. You know, magnitude if known. Sometimes you can't, right? Sometimes you don't know the magnitude for tension, for example. Then, you know, you probably also want to identify important information like mass and radius if known. Now, a common mistake, a lot of the time mistakes, you know, a lot of the time the question might tell you, for example, the length of the string is 10 meters, say. And a lot of people then think that's the radius of the circle. So that's a common mistake. So, you know, you need to actually find the radius. So the radius is not equal to the length of the string. Well, you know, unless it's horizontal, right? You get what I'm saying. You just need to, you can't assume it's the length of the string. You need to think about the situation, right? So that's one common mistake you might find there. Once you've identified all the forces and so on, your next step is to draw your free body diagram, which of course needs to show all that information. Your next step, of course, is to, you know, decide on your directions and then break down into components. Okay, and then once you've done that, then your job is to basically use F equals ma in each direction. And, you know, the directions will, one of them will always be towards the center, and the other one will always be perpendicular to that. Now, there's 2 options with that, but, you know, usually you'll be going vertical and horizontal. Okay, and, you know, do your analysis separately. So obviously towards the center, your acceleration will equal AC, and this acceleration will equal, well, unknown, but usually 0. But I can't guarantee that. That depends on the question. And so basically that's what you do. And then, you know, you just, and then you do algebra, right? Then you solve for what's required. And often that involves simultaneous equations. So those are basically the general steps. The steps don't change. The situation might, you know, they could give you what I said, like a conical pendulum. They could give you, you know, this bang track situation being the most common ones. You could have a plane flying in a circle. You've got you've got bicycles going around in a circle. Could be anything, right? You've got particles going around in a circle with your magnetic forces. It could be anything. But as long as it's circular motion, you need to, basically just follow the steps. Okay. And if you have trouble with one of those steps, then maybe, for example, if you can't identify the forces, well, then that's what you need to revise. All right. If it's something for year 11, go and revise that. If it's, magnetic forces, then perhaps you need to revise your module 6 or module 4 from year 11, right? Depends. But you basically need to be, the steps don't change. But if you have trouble with one of the steps, you need to sort of go and work out what it is you're having trouble with and why, and address that. Okay. So common mistakes you might find is, people might assume that the length of the string is the radius, which is not necessarily the case. And it is definitely not the case in my example here, right? This, in fact, R must equal L sine 30 in my case, right? Other common mistakes are you might, forget to, you might use AC instead of FC. So, remember AC is not equal to FC. And if you're doing, sum of forces equals MA, then basically, must equal FC, all right? So there's a difference of M. So don't forget to take mass into account, okay? When you're dealing with forces, it's either mv squared over r for the force, or it's m times, v squared over r, right? Other mistakes are, you must use, like you're not converting to SI units. All right, so pay attention to the fact that the mass obviously is in kilograms. Any distance is in meters. So, if you've got string in centimeters, you have to change that to meters. Any velocity is in meters per second. If you're using, angular velocity, then it has to be in radian per second. Okay. Those are probably the key common mistakes that you might find. Okay. But otherwise, yeah, that should basically cover it for circular motion as far as the theory goes. Obviously, that doesn't mean you know how to do the questions, and I'll leave you to do that, to practice sort of today here. Does anyone have any questions at all? So at this point in time, we have covered the, we've covered projectile and circular motion. And what is really left is, applications, to sort of satellites. Now, projectile motion is relatively less applicable, but what we'll need to know for satellites is, well, firstly, what a satellite is. And, a satellite is basically just something that goes around Earth, and we'll give it a circular path around Earth, which we'll call an orbit. And so the satellite kind of just goes around the Earth. This is not to scale, okay? Now, when we've got this sort of applications to satellite like this, then basically what we'll end up having is that we will simplify by assuming orbits are circular. So for many of the orbits that you do, that you are studying, they'll be close enough to circles that it's reasonably accurate. In reality, they aren't circular, but it will, because Kepler's, second or first law tells you that they're ellipses. But for your calculations that you're doing in physics, you're not expected to know about ellipses for calculations. And so you don't need to worry about that. So we're going to assume they're circular. Now, what you basically need to think about is the fact that, well, if you've got an, satellite going in orbit, one thing that you may or may not understand is that if you've got a satellite, you kind of, obviously get a rocket to shoot it up, right? But satellites are meant to stay up there for quite some time, like a few years, okay? Now, when it's going around the Earth, you need to think about if the rockets are on or not. Now, if you think the rockets are on while it's going around the Earth, because, you kind of think, okay, well, it's got to go around the Earth, it's got to have a force, and you need, it's like your car, right? You might think that you might have, your car has to run with your engine on, otherwise it's not running. Well, if that was true, then you're saying that you basically need to carry like years of fuel on the rocket, which is not feasible. You can't. You just can't carry that much fuel. So what actually ends up happening is what you do is you launch the rocket, it kind of goes up in a sort of spiral shape. This specifically will leave out. But once it gets in orbit, you turn the rockets off. And it stays in orbit with no force from the engine. So importantly, you need to understand that the aim of the orbit is to stay in orbit without using, engine thrust. And if you think about this, something in orbit, then it's probably quite clear that, it's going to have gravitational field, a gravitational pull. So there's a gravitational force pulling it towards Earth. And this gravitational force towards Earth is the only force we're saying acting on the satellite. And because the satellite is going in a circle, we're basically saying, assume only gravitational force. On the satellite. Now, Fg, you can calculate using, G m1 m2 over d squared, which is, Newton's universal law of gravitation. You can look up, the constant, which is 6.67 times 10 to the negative 11, but it's on your reference sheet as well. I hope you guys all know what that, all those things mean. And just reiterating again, D is in meters, all right? Sometimes they give you things in kilometers and students forget to change them and, well, you'll get the wrong answer. So the satellite is experiencing this force from the gravity. So it's G m1 m2 over d squared. But what it's also it's going in a circle. So what that means is that it must have a centripetal force, which is mv squared over r. Okay. And because we're saying it's going in a circle, it's not it's not sort of, if the net force is not equal to the centripetal force, then something weird will happen. Like it'll spiral in or it'll spiral out. It won't stay in a circle, is what we're saying. And more specifically, if the net force is greater, it will go in. It'll get pulled towards Earth. If the net force is smaller than the cost, than the requirement, then basically you can't stay in the circle and you start sort of veering out. Like if you're thinking about it like a car, you can't turn. You'll lose control, right? Or if the force is too large, you'll turn too fast, right? But if you want to stay in the orbit, you need these to equal. So in other words, what I'm saying is, for a stable orbit, you need Fg to equal Fc. That is the condition. And if you solve for that, I'll leave that in the maths here. You can kind of do that yourself. You can solve for V to equal 2 square root gm over r. And we call this the orbital velocity. And that is applying our theory of, circular motion to satellites to get the orbital velocity. So that's how we derive that equation. You can do the maths itself, but those are the formulas, the concept. And if we focus on orbital velocity for now, think about what that means. So, you know, V is orbital velocity, which, to be clear, is the velocity required for, you know, a satellite to, you know, remain in stable orbit. That's what orbital velocity means, right? It's the particular sort of velocity you need to sort of stay in orbit. But you can see that it's equal to the square root of g, which is a constant, so that's never going to change. Mass of the planet and r. So r is, you know, the distance from the center of the Earth. So in case it's, well, r is the distance to the center of the planet. So r is, you know, the distance between the, you know, two centers of masses, if you're being more specific, but normally we just think of the center, between the two centers of the objects. So, you know, simplistically think about it as, you know, distance to Earth, to center of Earth. So there's a few things we might want to clarify while we're talking about this, and we'll use this formula here. So this distance here is what I'm talking about. From the center of Earth to that, that's r, because that's the radius of your circle. Now that's different from this thing here, which is, this is the surface of Earth. So the distance from the surface of Earth to, you know, that, this is called altitude. So you may be given things in terms of altitude, but you need to understand that the orbital radius is, you know, you need to add, you know, the radius of Earth on top of that. And, you know, make sure it's all in meters. Okay, make sure it's all in meters. Okay. And so you can probably quite see that as mass of the planet goes up and nothing else changes, orbital velocity goes up. As the radius goes up, orbital velocity actually goes down. But even more importantly than that is that, because r represents the distance from the center of the Earth, more importantly is for a particular altitude. You know, if you want your orbit, you know, if you want your satellite to be at a particular sort of height, right, which is the altitude, you must attain, you must, you know, achieve a particular orbital velocity. No higher or lower. You go faster or lower than that, you're not going to stay at that height. Okay. You must maintain that particular orbital velocity. All right. Good. So that's orbital velocity. Now we'll probably also need to understand the concept of gravitational potential energy, which before we do that, let's just quickly do another thing, calculation of G. So there's going to be a few pieces that I'll need to sort of talk about, and then I'll put them together to talk about sort of, you know, gravitational potential energy and so forth. So calculation of G, recognize that Fg equals G m1 m2 over d squared. And this is gravitational force, but recognize that W must equal mg as well, where, you know, we say G is about 9.8 on Earth. But recognize that these two formulas, you know, are really describing the same thing. I mean, if you think about it, if you're on Earth and, you know, you're here, then you've got a weight force pulling you into the center of Earth, but that's just your, you know, gravitational field, right? So really, we can say that Fg must equal W on the surface. If you're, you know, on the surface, they're equal. And so that's our condition. And if you work, if you equate the two things there and then just, solve for G, hopefully it's quite clear that G must equal G times mass of the planet over D squared. Well, where D in this case would end up being, the radius of the planet, because that's how far you are from the center. Okay. So that's one thing there. We also need to talk about gravitational potential energy. Now, gravitational potential energy, you've done in year 11 using MGH. You might recall that we calculated that by using work equals force times displacement. And because the force was equal to mg times h, that's why it's mgh. And that was your change in, your work was equal to your change in GPE. And because we said GPE equals 0 at the bottom, therefore your GPE equals m times g times h. So, you had a simple situation where you had this kind of idea. So, object GPE equals 0, height equals 0, you move it up by some height here, and then you go, okay, I move it up. So therefore my GPE equals mgh. That's kind of what you did in year 11. But that's no longer sort of okay for year 12 in the situation with Earth for a few reasons. And the key reasons that, the upgraded version in year 12, we need to upgrade. And the key reasons are, well, one, force you said was mg, okay? Because you're saying that the force you need to apply is the same. Now that might be true for a few meters or even 100 meters or something, but the thing is this, you assume G is constant. You assume G doesn't change. But we just showed that it does, okay? When you're near the surface of Earth, who cares about that little difference? But if you're talking like, thousands of kilometers, well, that's a different story. This is no longer accurate. So the problem, of course, is that G, or the force required, is not constant and is significant over large distances. And the other problem with setting G equals 0 here is, well, see, gravitational potential energy is meant to represent how much potential energy you've got. And if you're telling me that G equals 0 is, you've got no gravitational potential energy, then, well, you're basically saying that this thing can't fall. So that's not really true though, because if you think about like this being a table and this is the ground, okay, it falls to the ground. But if your ground is on like level, 50 of an apartment building, it can still fall a long way down. And, if it gets to ground level, you can still fall down a drain. You can still dig a hole. Even if this is a ground, you can still dig a hole and make it fall further down. So it's not really true to say GP equals 0. So I won't really get into sort of all the sort of technicalities there. The real key point you need to know is that the other problem is we need to change the reference point. So we set GPE equals 0 at infinite distance away. And that basically helps work for any object, because what if you've got Earth and the sun, right? So basically as far away from everything as possible is where GPE equals 0. And that kind of ties in with the concept, because if you think about concepts before, as you go up, GPE increases. As you go down, GPE goes down. So extending that to sort of Earth here, the further out you go, GPE goes up. The more close to Earth you go, GPE goes down. But if we set GPE equals 0 at infinite distance away, and as we get closer to Earth, our GPE is going to go down, then the important result you need to understand is that your GPE, otherwise denoted by the letter U, is always negative for all points in the gravitational field. And, you know, you can do the calculus, especially if you're comfortable with it. But basically, you calculate GPE by integrating the force against X. We won't really need to do that here. I'll just tell you the result. But basically, this is going to be your answer. But basically, you can integrate this thing here against distance. But that's your GPE formula. So we now use that to basically prove the concept of escape velocity. So what is escape velocity? Well, escape velocity is the basically the minimum velocity required to launch a projectile such that it can escape the gravitational field Now, because of the fact that we're trying to sort of escape the gravitational field, then what we're basically saying is that you think about it, right? You're launching a projectile. So you're launching a projectile. What that basically means is that, you're giving it kinetic energy, right? So you're giving it kinetic energy, and remember GPE is negative, and it's negative G m1 m2 over r. And you're basically giving a k, which must always be positive, which is half mv squared. And so basically you're trying to sort of escape the gravitational field, right? And so this is kind of like being in debt. So you need to figure out just how much in debt you are, and you're giving it ke, all right? And so here's the thing. So what we now need to do is that we need to, well, work out how much money we need to give to make sure someone's not in debt. So what you basically then need is you need ke plus GPE to be positive or equal to 0 for the minimum. And this is our condition. All right? So we basically solve that, all right? And once we solve that, we can then basically use that to then find escape velocity. And you'll find that escape velocity equals square root 2 gm over r. And it might also be helpful to recognize it's root 2 times orbital velocity, which means it's greater than orbital velocity. And that kind of makes sense, right? Because, if you've got an object that's orbiting, then it hasn't escaped the gravitational field, obviously, right? It's relying on the gravitational field to keep it in orbit. So it hasn't escaped, right? But, because of the fact that, it hasn't escaped, that allows it to stay in orbit. But if you're escaping, then you obviously need to, throw harder. Now, obviously, if you throw harder than this, then, you escape anyway with excess speed. But if you have this minimum, it just means that the object you'll never come back. It will always just, keep going slower and slower and slower towards, infinite distance away. But it will always keep moving. In other words, the gravity can never stop it. Because, if you manage to stop it, well, it's coming back, right? So it can't stop. Okay, so there's other things that we need to sort of cover just quite quickly. You've got Kepler's laws, and we'll focus really on Kepler's third law. I mean, there is a first law and a second law, but you're not really tested on that too much. I mean, first law is, I'll just tell you to save time and space, but first law is just, all orbits are ellipses, all right? And the focus has the center of mass there. And the second law is basically law of equal areas, which you're basically never tested on. But basically, it's just, you know, the thing from that is it's the law of equal areas. But you can basically take it that if your orbit is, if you're closer to the star, you move faster. If you're further away from the star, you move slower. But, you know, given you're assuming everything is circles, then there's no difference. The radius is the same. Now, you do need to know the third law, which is also known as the law of periods. And you do definitely get questions on these. And the law of periods basically say that r cubed equals t on t squared equals k, a constant, you know, for, you know, objects orbiting the same mass. Okay. So if you have all objects orbiting the same mass, then there's two ways to use this. So one is to use r1 cubed over t1 squared equals r2 cubed over t2 squared. So basically we're saying, you know, compare two different objects, all right? Compare two different objects. You know, one is, for example, Earth, which is going around the sun. One is, for example, Mars, which is also going around the sun. Compare their radii, compare their times, and they should, you know, as long as you know 3 out of these 4 things, you can work out the 4th. So technically, the SI units, of course, R is meant to be in meters. T is a period, right? So it's meant to be in seconds. But just so you know, if you're doing it the first way, you're just comparing one object to another, you don't have to use SI units. You simply need to make sure that just as long as the units match. So, you know, if you're working in kilometers, then that's in kilometers. If you're working in years, that's in years. If you're working in astronomical units, that's in astronomical units. Like, and the reason for that is hopefully quite simple. Like, if you convert it to meters, you know, you'll get an answer in meters, then you can convert back. Like, the factors will just cancel out, right? The conversion factors will cancel out, okay? So if you're doing it this way, you don't have to use SI units. Now, the other way is to use r cubed over t squared equals gm over 4 pi squared. And for this one, you do have to use SI units, right? And if you're interested, this one is proven by basically, again, using Fg equals Fc and subbing in velocity equals 2 pi r over t. But basically, that is Kepler's third law. And probably importantly for you guys as well, you might want to just think about what that means. So Kepler's third law is that r cubed over t squared is a constant. So basically that means if r goes up, then t must go up. And obviously if r goes down, t must go down. So what that basically means is that you will need, you know, so for example, you know, we can do calculations with this, but what that basically means is the further out you are, you know, the longer it takes for you to complete one orbit. Yeah. Does it all make sense? So if that confuses you, maybe another way to express it is r cubed over t squared is a constant. So another way to think about it is r cubed equals k times t squared.
Okay, I got it. Yeah, sure.
And therefore, you know, as r goes up, t goes up. As t goes up, you know, as r goes down, t goes down, and vice versa. And but it, you know, this is a relationship between these things. And yeah, essentially, we're saying that, you know, the further out you are, the bigger your radius of your orbit, then the longer it takes. Which is why Pluto takes, you know, almost 300 years to go around the sun, compared to us, right? And there's no exception to that rule, right? You know, as long as you're, you know, basically using Kepler's third law, you're following orbits, you know, and assuming you're only going around one thing, then it's going to be that. And I might also mention here, because I didn't really get the chance to point it out earlier, this mass here is going to be the mass, not of the planet, but, you know, of the thing being orbited. So, you know, of the mass of the object in the center. So if I'm looking at, you know, Earth and Mars and Venus and so on, then this will be the mass of the sun. On the other hand, if I'm talking about like, you know, the moon of Earth and a satellite, then this will be the mass of Earth. It's whatever the, you know, things are orbiting. Great. So it looks like there are no further questions with that.